Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Formally, greetings, grade 11s. Welcome to paper 2 revision today. For a lot of you, paper 2 is coming up towards the end of this month, November. And for one person in particular, their paper 2 is coming up tomorrow. So this is a very important session. We are looking at the 2020 paper, last year's November paper of the Eastern Cape Education Department. So the Eastern Cape learners wrote this paper last year, grade 11. Shout out to them and thank you to them for allowing us to use their papers. But we're going to have a look at paper 2. We've looked at paper 1. We conquered paper 1 of the same here. And now we're going to have a look at paper 2 now. Okay, so we're going to start off with question 6 because these are some of the major areas in the paper that's going to be in you guys' paper 2. And where we maybe just need some more exam practice and maybe under a little bit of pressure, because in the exam there's going to be a lot of pressure. Okay, because you're writing for about, I think, 3 hours or 2.5 hours or 2 hours, depending on how long the paper is. If it's 100 marks or 120 or 150 marks. In grade 12, it'll be 150. So we're going to start here on question 6, which is the beginning of the stoichiometry section. Okay, I'm not going to read it out loud because it's all very plain and simple. I'm sure you all can read. So I'm just going to leave that on the screen, and we're going to begin with question 6. As you can see, the instruction is to start on a new page, something that we must watch out for grade 12, as most of the instructions or questions will need to begin on a new page. Okay, so I'm going to scroll down just so we can see 6.1, and let's do up until 6.2.2 first, and then I'll scroll down to 6.3, which is a 5-mark question at the bottom. Methylpropanoid, okay, which is an organic compound. Some of you have already touched organic chemistry in grade 11, but it is a grade 12 topic where it's taught in its entirety. But methylpropanoid is an organic compound with the following percentage compositions: 54.55% carbon, 9.09% hydrogen, and 36.36% oxygen. The molar mass of the compound is 88 grams per mole. Now, just a note quickly, because remember we're going through this paper step by step and looking for hidden gems, so to speak. 88 grams per mole is the molar mass of the molecular compound. Okay, they don't tell you that though, but it is the molar mass of the molecular compound. In other words, the compound that exists in 100%. In other words, it's not its empirical formula. It's not the simplest whole number ratio. Okay. 6.1.1, define the term empirical formula. And I'm sure we can all define the term empirical formula. Okay. But I'll define it for you all one more time. Okay. Empirical formula is basically the simplest whole number ratio. Okay, now to add on to that, simplest whole number ratio of elements given in a compound. Okay, or elements in a given compound, whichever one you want to use. Okay, but you can't just say simplest whole number ratio. That's a way to remember it though. Okay, but you need to mention the simplest whole number ratio of elements given in a compound. Okay, now 6.1.2, that was the nice question that we all know so well. Determined by calculation the empirical formula, and that is for 6 marks. Okay, so what do we need to do? We first need to calculate what's the number of moles. So we all know the formula for the amount of moles is equal to mass divided by molar mass. So we can say, well, underneath here, the number of moles of carbon is equal to, of course, this is all in 100 grams. So that's 54.55%. Basically, it's 54 grams, or 54.55 grams, all divided by the molar mass of carbon, which is 12. Okay, That's going to give us about 4.55 mole. And then we can take the molar mass of hydrogen, which is equal to 9.09, all divided by about, well, 1. That gives us 9.09 mole. And then we've got the last one, moles of oxygen, which is 36.36, all divided by 16, and that's going to give us 2.27 mole. Okay, so of course what we've got to do, we've got to split these up into ratio, of course, of 4.55. Well, let's do it on another page, sorry. So we've got the mole ratio of carbon is to the mole of hydrogen is to the mole of oxygen, and that's obviously 4.55 to 9.09. That looks like a 6 there. Let me just fix that. 9.09 is to 2.27. Now 2.27 obviously looks like that's the simplest ratio, so we're going to divide them by 2.27. Okay, and I'm doing this out in full. Okay, now once we do that, of course, we'll get an empirical formula, or a ratio, a whole number ratio of 2 is to 4 is to 1. Alright? Easy. Okay? Now that we know that, all we're going to say is, now let's take the empirical formula. Alright? In our final answer, empirical formula, colon, or we can say empirical formula is, well, that's carbon, so that's C2, and there is H4, and that's just 0. You don't have to write 0, 1. You just sorry, not 0. Oxygen. You don't have to write oxygen with the 1 there. That's intuitive. Okay. Now there shouldn't be any questions on this one because we have done this throughout the year. All right. Hopefully we didn't make any silly mistakes on this one. Okay. So we'll just jump straight to the next question. 6.1.3, which was determine the molecular formula now. Well, that's very easy. We have to take the ratio of our molar masses. So we were told that the molar mass of the compound, or should I say the molecular formula compound, is 88 grams per mole. So we take the ratio and we say that is equal to the molar mass of the compound, all divided by the molar mass of the empirical formula. Okay, or we could say formula mass, which is going to equal, of course, 88 grams per mole, as it told us in the question, divided by 44, which is the molar mass of this compound. 12 times 2 plus 1 times 4, which is 12 times 2, 24, plus 4 is 28, plus 16, 44. Okay, now that we got that, can it give us a ratio of 2? Okay, well, on this side, therefore, the molecular formula, okay, I have to write that underneath like this, molecular formula, basically, it's going to equal this entire empirical formula multiplied by 2. So it's going to be C4H8O2. And that's the molecular formula of methylpropanoid. 6.2 say learners prepare a solution of sodium hydroxide NaOH in water by placing 8 grams of sodium hydroxide in a volumetric flask and adding water to produce 250 cubic centimeters of solution after stirring. Okay. Define concentration in words. Now, this is another definition also worth 2 marks. Now, concentration we should all be familiar with, so I'm not going to go ahead and write it, but I'm going to say it audibly. Okay. Concentration is the amount of solute per liter, or the amount of solute per volume of solution. Okay, the amount of solute per liter, or the amount of solute per volume of solution. Now, That should be quite intuitive when we learn concentration. Okay, any other definition along those lines shall be accepted. Alright, 6.2.2 says calculate the concentration of sodium hydroxide in the solution. Okay, now this one wasn't very difficult. We were told the volume in any case. We were also told the mass as well. So remember, we got a formula for 6.2.2. We got a formula for concentration that C is equal to number of moles divided by the volume. Okay, but we also know that the mole formula is N is equal to M divided by big M, or mass divided by molar mass. So as you can see, we've got N present in the formula. So therefore, we can form a joint concentration formula to say C is equal to the mass divided by the molar mass multiplied by the volume at the denominator. That way we can perform one sum instead of this one first and then plugging it into the concentration formula. So we can basically just do 2 in 1. So let's have a look at that. They told us 8 grams of sodium hydroxide. We know that the molar mass of sodium hydroxide, sodium is about 23, oxygen 16, and hydrogen 1. So 23 plus 17 is in essence is 40. So we got 40 for the molar mass of sodium hydroxide times the volume, which is 250 cubic centimeters, but we're going to convert that to decimeters cubed. So that's 0.25, and therefore the concentration of sodium hydroxide is 0.8 mole per decimeter cubed. That's our final answer. 6.3 says sodium azide, NaN3, is used in car airbags. For the airbags to inflate, the following action must take place. NaN3 solid becomes sodium solid plus nitrogen gas. Calculate the volume of nitrogen gas N2 that would be produced at standard temperature pressure if 55 grams of sodium azide reacts completely. Okay. Nothing to panic about. First thing, let's find the number of moles of sodium azide. NaN3, that's equal to mass divided by molar mass. Let's do it all in a straight line. That should be, they say, 55 grams. Well, that's 23 plus 14 times 3, that's 42. So 42 plus 23, that should be about 65. Now that should leave us with 0.85 mole. Okay, so that's the number of moles of sodium azide. Now we have a mole ratio of sodium azide to nitrogen gas, because that's what they want to know, how many, what's the volume of nitrogen gas that was produced. So we know that's a mole ratio of 2 is to 3. So if we want to find out how many moles of nitrogen gas was produced, if we've got moles here, this is N ratio. Okay, then we've got the number of moles here. That's going to obviously be 0.85. So if you want to find out how much moles of nitrogen gas was produced, we'll take the actual divided by 2 multiplied by 3. Okay, divided by 2 multiplied by 3, which is the same as times it by 3 over 2. That should give us 1.275 mole. Okay, so therefore number of moles of nitrogen gas that was produced is 1.275 mole. Okay, now that we got the number of moles of nitrogen gas, we should remember this formula. N is equal to the volume divided by the molar volume. Alright, so we got the number of moles, alright, which to be 1.275. That should equal to V divided by molar volume is 22.4. We all should remember that. So obviously we're going to multiply these two together, okay? And therefore the volume of N2 gas that was produced should equal to roughly about 28.56 decimeters cubed. Question 7. The fertilizer ammonium sulfate NH42SO4 is produced from the reaction of sulfuric acid and ammonia, okay, according to the balanced equation. Okay, H2SO4 plus 2NH3 gives us NH42SO4. 2 kilograms of sulfuric acid and 58,82 or 58,82 moles of ammonia are available to produce the fertilizer. Define the term limiting reagent. All right, now we'll define it audibly again. Don't write it down. The limiting reagent is the substance that is completely used up in a chemical equation. All right, we've learned this already before. I'll say it one more time. It's the substance that is completely used up in a chemical reaction. Okay, so I'm going to go through this at a quick pace because we're running out of time for the live class. So let's see if we can get through maybe at least question 8. I'll be happy if we can get at least through question 8 before we end off the session. But let's do 7.2, which is calculate the maximum mass of ammonium sulfate that can be produced by the reaction. All right, so judging by that question, it's probably going to make use of a lot of mole ratios and actual moles, etc., etc. So first of all, for 7.2, didn't realize I was in this color, but let's just keep going with it. Let's calculate the number of moles of H2SO4 that reacted to be, okay, well, that's the mass was 2 kilograms, which is 2,000 grams. Remember, in chemistry we use grams and not kilograms. In physics we use kilograms. And the molar mass of H2SO4 we calculate from the periodic table. So let's calculate that. We know it's equal to M over big M. And periodic table quickly, that's 2 plus 16 times 4 plus, forgot what is sulfur on the periodic table. Just give me a second. Sulfur is roughly about 32, so that should be about 98. And therefore, number of moles should equal 20,41 mole. Okay, so what we want to do is want to take a mole ratio of H2SO4. So let's just take ratio here of H2SO4. In fact, we don't even need to write that out. H2SO4 to NH3, we know already is 1:2. Okay, so therefore, if we want the number of moles, we know this is 20,41, and so we need to divide it by 1 and times by 2, which is basically just 20,41 times by 2, and that should give us about 40. Am I right? Yes, that should give us around 40,82, if I'm correct. 40,82 is correct. Okay, so we know our ratio of basically H2SO4 to ammonia is 1/2, right? This is the same as a half, 1/2. It's the same. Okay, so let's compare our actual mole ratio. Okay, so that was theoretical. Let's actually take our actual mole ratio, and that's going to be 20,41 over 40,82, and that ratio is basically going to equal 20,41 divided by 40,82. It's going to equal a half as well. Sorry to the learners, I missed the fact that they'd already given us the amount of moles that was available. Okay, so in actual fact this should be 58,82. Sorry Alex, was that what you were trying to tell me? I think so.
Oh no, I was so confused.
Oh no, okay, cool. Oh, we're both confused. Okay, cool. Well, now we are both unconfused. Okay, so in decimal, this half basically is 0.5, right? So if we're taking theoretically this amount of moles that should be reacted, and this is the amount of moles that was available of ammonia, are available to produce the fertilizer. So we calculated theoretically with 20,41 moles. Theoretically, we should have used only 40,82, but we actually were told that 58,82 was available. So without even doing this calculation, which I'm going to do now, we see that this ratio is 0.34. All right, if you round off to 2 decimal places. So this ratio, we can see, is smaller than our mole ratio. Our mole ratio is 1:2, which is basically 0.5. And also theoretically, we should have gotten, if our mole ratio was exactly half, then we only needed twice as much to react, but we got a little bit more. So our limiting reagent, because our ratio of our actuals is less than our theoretical, right? So therefore, we can state that H2SO4, which is sulfuric acid, is the limiting reagent. In other words, all of it, all 20,41 reacted. Now that we got that, we know that's the limiting reagent, okay? We need to calculate now the maximum mass of ammonium sulfate, okay? Now, that's great and whatever. The maximum mass of ammonium sulfate, first of all, ammonium sulfate, brackets NH4, 2SO4, okay? We know that the moles is equal to 20,41 because of the mole ratio is 1:1. Sorry, 1:1. We know that from the reaction. Okay, 1:1. And we calculate the amount of moles of sulfuric acid. So let's add that in there. So we want, therefore, mass is equal to the amount of moles times the molar mass. So the amount of moles was 20,41 multiplied by 132. Okay, so we find out that nitrogen is 14 plus 4. All right, that's equal to 18 times that by 2 plus 32 plus 16 times 4. That's 132. And we do 20,41 multiplied by 132. Oh, sorry, I typed in 135 times by 132. We get an answer for the maximum mass to be 2,694,12 grams. All right. And that's our final answer. So in the previous slide, we worked out, okay, the amount of moles of H2SO4. So we can find out the limiting reagent. Okay, if you want to find out what is the limiting reagent, now that we've got the limiting reagent, we can obviously go and, or that we even, with that we've got an amount of moles here, we can jump now straight to the final answer, which is to calculate the maximum mass of ammonium sulfate that was produced. Okay, which is, and this is the way we calculate it. Pretty basic, pretty simple. So question 8 is the acid and base question, especially in this paper. It usually is around question 7 or 8. And here we got a chemical reaction. HPO4 2- plus water gives us PO4 3- plus hydronium. And all in aqueous solution except water, which is a liquid. Define a base according to Lowry-Bronsted theory. Okay, well now you got to just define a base, not the acid and base, just the base. Okay, very specific, cannot miss that. And the way we do that is a base is a proton acceptor. 2 marks. Okay, a base is a proton acceptor. 8.1.2 says write down one conjugate acid base pair in the equation. Okay, conjugate acid base pair in the reaction or equation. So let's pull that up one more time and let's have a look. That looks like that may be HPO4 2 minus and PO3. Of course, the other one would be H2O and hydronium. Okay, but you can pick whichever one. For 8.1.2, I'm going to pick that one. HPO4 2 minus and PO4 3 minus. They are conjugate acid-base pair. 1.3. Let's find out what that question was. Is the reaction mixture acidic or alkaline at the completion of the reaction? Please give a reason. Give a reason for your answer. Well, the reason is actually it is acidic. All right. The reason why we know that is because, and we can use the word excess. Okay, H3O plus. All right, ions or hydronium ions are produced. So we saw that there was a production of H3O plus. If we had OH minus at the end, it would be more alkaline. But it is because we see the presence of hydronium, we know it is acidic. Okay, that's one way to look at and determine whether a reaction is more acidic or alkaline, which would be more basic. We don't use that term though. 8.1.4, write down the formula of a substance in the reaction other than H2O that can act as an ampholyte in some other reactions or in some reactions. Okay, well, if we look at the reactions, that would be HPO4 minus. 2 minus, sorry. This is an ampholyte that can act either as an acid or as a base. Okay, that's what an ampholyte is. Now, water is the most common ampholyte. It can act as acid or base, but another one being HPO4. In other words, HPO4 can still accept another 2 hydrogen protons. All right, it can still accept another 2 hydrogen protons because we see it's got 2 minus, so it can take another 2. Okay, it can also accept, and as well as we see in the current reaction, it gave 1 away. So HPO4 2 minus, we should have recognized, is an ampholyte. Okay, now 8.2 says copper oxide reacts with nitric acid. Okay, write down a balanced chemical equation for this reaction. This is grade 10 work, basically. We learned how to balance equations. Now copper oxide, yes. So we have CuO plus nitric acid, which we know is HNO3. And now we need to determine what are its products. Okay. Well, I think we're going to get CuNO3. Okay. Now we know nitrate is a -1 ion, and it said copper 2, so copper made 2 bonds, so that means it's going to be like this, and plus water. Okay, we're going to have that plus water. And now we need to balance the equation, so we've got 2 hydrogens, and we also got 2 nitrates, so we just need a 2 in front of HNO3, and then we are balanced. Okay, and that's the balanced equation, all done and dusted. Okay, let's move on. Okay, so we didn't see 8.3.2, but let's see what we can do with 8.3.1. 8.3, 40 grams of impure calcium. Okay. Calcium carbonate reacts with 200 cubic centimeters of a dilute sulfuric acid with a concentration of 1.5 moles per decimeter cubed. All the calcium carbonate and sulfuric acid react completely, leaving the impurities unreacted at the completion of the reaction. And then we get the reaction there. CaCO3 plus sulfuric acid gives us CaSO4 plus carbon dioxide plus water. Calculate the percentage purity of the calcium carbonate. All right, 6 marks. Okay. This one we'll do, and I think that'll take us through to the end of time here for the live class. So let's take this away here. 8.3.1. So firstly, let's react the acid, or find the number of moles of the acid. Okay, which is obviously the concentration times the volume. Okay, so which is going to be around 1,5, which is the concentration of sulfuric acid, as it says there, right? Let's see. Yes, 40 grams of impure calcium carbonate reacts with 200 cubic centimeters of a dilute sulfuric acid with concentrate. Okay, great. So you have to calculate the amount of moles of the acid. So 200 cubic centimeters divided by 1,000 to get it into decimeters cubed. All right, that's 0.2. So 1,5 times 0.2. 1.5 times 0.2. That gives us 0.3. So we've got 0.3 mole. Okay. Let me just check one thing out quickly. Times. Yes, I'm right. Okay, cool. So we get 0.3 mole. Okay. Now let's calculate the mass of calcium carbonate that is used, because we've got everything to be in the same mole ratio. So let's calculate the mass of calcium carbonate used. CaCO3 that is used is going to equal, of course, the number of moles, times the molar mass. So that's just the mole formula manipulated. Okay, so we're going to have 0.3 moles because they're in the same mole ratio. Okay, multiplied by the molar mass there is 100 of calcium carbonate, 16 times 3 plus 12 plus 40. Okay, and that should give us, let's see, 0.3 multiplied by 100 should give us 30 grams. Okay, so remember it said 40 grams of impure calcium carbonate. All the calcium carbonate and sulfuric acid react completely, leaving the impurities unreacted at the completion of the reaction. All right, calculate percentage purity. So what have we calculated? The amount of moles of the acid that reacted completely with that concentration at volume. We're calculating the mass of calcium carbonate that was actually used in the same mole ratio, okay, with the same amount of moles. All right, we get 30 grams. So percentage purity is taking our actual amount that was used, 30 grams, dividing it by the 40 grams, which is the mass of the impure, multiplying that by 100 to get a percentage. Okay, and therefore percentage purity is equal to about, well, 30 divided by 40, which is the same as 3 over 4, is 75%. So it's only, this compound calcium carbonate is only 75% pure. All right, 25% impure, which is basically 10 divided by 40. So about 10 grams is impure, basically. But they asked for percentage purity. And grade 11s, that's my time for this evening. Thank you so much for joining me here in class. We didn't get to finish up until question 10 as time was against us, but we will complete that in the next session in the final week. So we'll complete this question paper, especially of these big topics that do challenge us a little bit. Until then, please don't forget to like, comment on this video, as well as subscribe to our channel. And as always, we'll catch you in the next tutorial.